Welcome to the updated tutorial on doing concentration filtering in 3Depict. I'm going to show you how to open the file and figure out the random concentration distribution first, and then we're going to figure out the real one and compare them. So first we're going to open a POS file. Here we see them loaded with the default color, which is red. I'm going to stick a range file on that, select the POS file and select range, and open the range file. And now we've got our ions. We can disable ions in the range filter, so disable the ions. We can see we've got some copper ions here which have some sort of structure to them. I find a good first step in finding out whether there's something happening in the data is actually to use a new feature in 3Depict in the voxelization, which allows us to see the concentration. So often in Atom Probe we look at the density of the points rather than the concentration. Using a voxelization process, voxelizing the data, we can actually get the concentration. So here we want the concentration of copper. Using all the ions as a denominator, so we get concentration. I am going to put a threshold mask on, and this just means we've got to have at least 2 ions in a voxel for it to count. I'm going to add some Gaussian smoothing as well, and I want this rendered as a volume render, and that's what I want to show you. So if we hit refresh now, you can see now we have this lovely looking data set. We can disable the axes, view axes, and we can see there's clearly some shapes going on in there that's what we want to identify. So this is looking at concentration space. So this is going to be what we're filtering out when we apply the concentration filtering. Right, so now we're done with the voxelization. We can get rid of that. First of all, we're going to randomize the data and look at what the threshold for a concentration filtering should be. Now, we could use the voxelization, but that's not going to be exactly the same measure. So we want to use exactly the same technique for both. So we're going to load the data. Then the first thing we do is we're going to do value shuffle the masses. So now when we range this, if we look at where the copper is, let's hit auto refresh now, you can see we don't have that structure anymore. So the mass labels of the ions have been relabeled. So now we have our random data set. And to this, I turn auto refresh off here so it doesn't calculate it. I'm going to hit the spatial analysis. And this has got local chemistry calculation and local chemistry filtering. And it's the local chemistry filter we use in a moment. So first we're going to use local chemistry. We're going to set the stop mode to 0.5 nanometers. We want the source ions. We want it to operate on all the ions. We want it to work on only copper as the numerator. So it's going to give us copper concentration because the denominator is iron and copper. Now, to visualize this, we're going to need an ion color filter. So this is going to color our ions based on what concentration they have. And I'm going to change the bounds here because I know that I want to change those. We also want to output a spectrum. So this is going to be a plot of the value of our ions and how many of each of those ions have that value. Let's hit refresh now. Okay, so this is our random data set. So we're not expecting this to show anything in this case. And now we've refreshed, you can see we've got this exclamation mark. And that's just because we didn't unsample the data. So let's make sure that's unticked. And this is going to load all of the data from the hard drive now. Okay, it's a small file, so I don't think it makes much difference here. But this is what our filter data looks like now. So with these settings, that's what we've got with this concentration. And we can see we've got down here, we've got a histogram. We can change the binning on this. Maybe we want 1 instead of what it was before. This shows us that we've got our random data up to a level maybe about 20 or 30. There's still some points there which have got high concentration. There are a few points here that have got really high concentration, so that's because we're using a sphere, and these points on the outside don't have very many nearest neighbors in that sphere, so they seem to have very high concentrations. You could use a nearest neighbor count here instead. We're just going to stick for radius for now. So this is our random data. Let's rename that. So let's rename the spectrum to rand. That's our random spectrum. And we're just going to grab everything and make a copy. So I'm just going to collapse the filter tree, hit Control, drag and drop. And that gives us a separate copy of the data. And this one we're going to have as the real data. So I'm going to rename this real so we don't get confused. And I'm going to change the color. Oh, I don't want to calculate. Change the color. Let's have the real one be black. And instead of the value shuffle, I'm going to translate, and that means the data is not going to overlap. So let's just translate this by 18 and refresh everything. Now, hopefully, that should work. So we've got our real data and our random data, and they're shown side by side. We've got the comparison of the graph down here. We can see something's definitely happening in the real data. You can see there's many more points with a higher concentration. We can't see much difference really inside the data, and that's because we're seeing all of the points here. So we can crop this using the ion transform filter. So on the real data, after the spatial analysis, I'm going to stick an ion transform. This is just to visualize it. I'm going to do crop value, and we want everything above 20. And we're going to shuffle these filters around so our spectral color goes after the ion transform. When we refresh now we can see those features really picked out nicely. So these are only the ions above that concentration threshold, and we can play around with this. So maybe we want 10 for when we actually do our filter, and that's going to be the result that we get. So those are our filtered ions that are left behind after we do that filter. So what we're looking at here is concentration. And if we wanted to do a cluster analysis on this, it's not going to work because we don't have the ion identities of these ions. So first of all, before we do anything else, let's get rid of this crop. I'm just going to save this data. You know, it took a little while for us to create. Let's save it so that we have it for the future. So I'm just going to do File, Export Ions. I'm going to enable Selected Data because we only want the real data. We don't want the random data. And when we get to a filter which has got some data in it, you see it says available data down here. That's what we're going to copy across. And when we save that, it's going to output it here. So I'm going to name this torus 1.0.5 because we used a 0.5 radius and copper. And I'm going to call this conc. So this is the unfiltered data. This is 0.5 radius copper concentration, and that's how I keep things organized. So we've got that stored away for later. Now, let's just clean up. Let's clean up, in fact. Let's get rid of those. We've got the real data here. It's transformed, but we're not going to worry about that. Instead of local chemistry now, we can select local chemistry filter. And we can use exactly the same settings, except in the algorithm parameters here, we'll set a cutoff. We can set 10, and this is 10 atomic percent cutoff. And when we run this now, what we return is they're grey because we've not got any kind of filter to colour them. But if we look at a range file on top of that and refresh, now you can see we've got pink and yellow, which is our iron and copper ions as before. So now this is our real data set and it's been filtered. So this is a recently introduced filter that allows you to do the concentration filtering without having to export the file and load it back in again. So now we've got, this is basically a new data set which has been filtered. And if we wanted, we could pop some cluster analysis on that. We want copper to be our core range, and let's spit out the cluster ID. So this is going to color the ions by which cluster they're in, and that means we need an ion color filter. And I'm going to select pseudo random so that it randomizes it. And those are our different clusters. It's detected 52 clusters. You can see each of those. This torus here has been split up a little bit. We can just increase maybe 0.7. Let's put auto refresh on. We've got a whole bunch of smaller clusters around here. We can get rid of those with the size cropping. So this is like your n min in your cluster search. So we can just hit that 20. And there we go. We've got these 10 different objects which have been identified. We could include a bulk distance as well if we want. Then we could get, our morphology distribution out if we wanted. or we could get the cluster chemistry distribution. So we could plot how much iron and copper they've got in them. So this is each of the cluster size and what concentration they have, and whatever analysis we want to do. Get the positions, geometry, etc. So very, very useful to use concentration rather than just density on analysing your data.